Hello everyone and welcome to a new video. In this video we will be talking about something called the electrical fields. So we learned before that charges can charges can attract each other or repel, and there's a certain force between these charges, and we learned how to calculate this force using Coulomb's law. But now in this lesson we will be talking about what is causing this force. So charges can either attract or repel depending on their charge. We already know that. Well, the cause for this force, what's causing the cause of this force is something called the electrical field. So what makes these charges attract or repel is something called the electrical field. Now, electrical fields have a magnitude and a direction. And the magnitude of the electrical field depends on the strength of the charge, while the direction depends on the type of the charge. Now, if we go a little bit back, we said that any physical quantity that has a magnitude and a direction is called a vector. And we know that there's a force between these charges, and we also know that forces are vectors. So now it's like the pieces of the puzzle are getting together. We know that an electrical field has a magnitude and a direction, and we know that there are forces between these particles caused by this electrical field. So an electrical field is a type of force that has a magnitude and a direction. The magnitude depends on the strength of this charge, while the type of the charge affects the direction of this electrical field. Okay? Now, because electrical fields are invisible, we will be using lines and arrows to represent them. For positive charges, we will draw arrows that are going out of the particle. But for negative charges, we will draw arrows that are going towards the particle. So it's pretty easy and straightforward. The intensity of the lines, or the more the lines, that means the stronger the field. The more the lines means the stronger the field. So if we had a larger charge, it will increase the magnitude. So we can draw it, or we can represent it by drawing more arrows. Okay? But what happens if we get more than one particle close to each other? What are the patterns that we will get? So we can get many combinations of electrical fields. As an example, if we have a positive charge close to a negative charge, this is the pattern that we will get. So you can see here that the lines or the arrows are leaving out from the positive charge and going in towards the negative charge. Another example, if we get two similar particles close to each other, look at the shape of the field. Say we have two positive charges. We see that the arrows are living outside the positive charges. Look, we said that the more the lines, the larger the magnitude. But in this location here, we have no lines. This means that there are no electrical fields here. This means, in other words, that there is no electrical force at this point. So if I have a charge, a particle, or whatever, at this location right here, the force on it, or the electrical field, will be zero at this point, okay? Now say I have a plate, a steel plate that is charged, that it has charges on it, a positive plate and a negative plate. In this case, we have something called a uniform electric field. In a uniform electrical field, the electrical force is the same between the points at any location. So if I had a particle here, a particle here, a particle here, a particle here, they will all be affected by the same electrical field. Therefore, they will have the same electrical force on them. Okay? Another example, if I have a very large particle next to a small particle, you can see that we have a certain pattern of electrical fields for that too. Now, how can we find the strength of the electrical field itself? A very simple experiment was done to do that. So the strength of the electrical field was found by adding a very small test charge, and let's call this Q note. And we used a very small test charge, so it won't have any effect on the electrical field. So it won't disturb the electrical field, because we saw before that if we have two electrical fields, they will create a combined electrical field. So we are using a very small particle, so it won't affect this electrical field. And we were able to find the electrical field using this very simple formula. The formula says that the electrical field is equal to the electrical force divided by Q naught. And we said that Q naught is the charge of the small test charge. Or we can use this other formula that says that the strength of the electrical field is equal to Coulomb's constant multiplied by Q divided by R squared. What is E? We said that E is the strength of the electrical field and its unit is Newton per coulombs. And Kc is Coulomb's constant. We learned that before. And finally, Q is the amount of the charge causing the electrical field. And that makes everything clear for R. R is the distance where we want to test the electrical field. Because the further we are from the charged particle, the weaker the electrical field will be. And that's everything we want to say about electrical fields right now. Stay tuned in the next videos so we can solve some problems related to electrical field.